Hi everyone, welcome to my video report of Lab 4 Physics 2 class at Georgia Tech. In this lab, we focus on the concepts of electric circuits, specifically potential difference, current, and resistance. We completed two major experiments in this lab. In the first experiment, we built a simple series circuit to verify the charge conservation and energy conservation circuits. In the second experiment, we built a resistor-capacitor circuit or a RC circuit to learn the mechanism of such circuits. In this lab, we simulate all circuits using the provided online circuit construction kit. In the first experiment, we firstly built a circuit following the diagram on the top right, where two batteries, each with 1.5 volts, 2 ammeters, and 2 resistors, one with 47 ohms and the other one with 100 ohms, are connected in series. We can easily predict the current by computing the entire resistance in the circuit and applying the Ohm's law, and we have the current should be approximately 0.020408 amperes. Note that I1 should be the same as I2 by applying the node rule. This matches with the actual recordings from the ammeters in the circuit, which both display 0.02 amperes. Next, we replace the second ammeter with a voltmeter, and we find that the other ammeter displays 0 amperes and the voltmeter displays a value of 3 volts. The reason is that the resistance of voltmeter is very large, and the voltmeter is connected in series in the circuit, so there's almost no current in the circuit. Next, we measure the potential differences of each part in the circuit. Note that only the potential differences around the batteries to resistors are non-zero, while the potential differences of all other parts, including the wires and ammeters, are zero. These are the results from the experiments, and the readings were recorded into the table in the previous slide. Applying the loop rule, the sum of individual potential differences for a round trip around the circuit should be zero. Our measured differences verify that, as shown in the slide. When the voltmeter is attached in parallel, this will not affect the readings of the ammeter because the current will mainly go through the route of resistor due to the extremely large resistance of the voltmeter. However, it will be different if we connect the ammeter in parallel with a 100 ohms resistor. This time, the current will mainly go through the route of the ammeter because the resistor has a much larger resistance compared with the normal ammeter. We only need to consider the 47 ohm resistor for the current circuit, and this is why we have a larger current in the circuit, which is 0.06 amperes. Also, using the measured voltage differences and the current values, we can compute the resistance for each resistor and wire in the ammeter. Applying the Ohm's law, we can see that the computed resistance is roughly the same as displayed value for each resistor, and for wire and ammeter, they have zero resistance. In the second experiment, we built a resistor-capacitor circuit where we connect a battery with 9 volts, a bulb with 10 ohms, and a capacitor with 0.2 farad in series. When the circuit is closed, we can observe that the light bulb is lit first, and then becomes dimmer, and then there's no light in the end. Next, we remove the battery from the circuit, and we connect the capacitor directly to the bulb, as shown in the diagram. We observe a similar result where the light bulb is bright at first, then it gets dimmer until there's no light. We also measure the time it takes to charge the capacitor and discharge the capacitor, both with 9 volts battery, while one with a 10 ohm bulb and the other with 20 ohms bulb. The results are shown in the table. We can see that the time with a 20 ohms bulb, both charging and discharging, is about twice as the time with a 10 ohms bulb. Then we analyze the time dependency of the voltage difference around the capacitor by using a 30 ohms bulb to discharge a 0.2 farad capacitor, which is previously charged by a 9 volts battery. We record the voltage difference of the capacitor with a voltmeter, and on the right are the measurement results. We want to compute the RC value in the circuit, and by applying the loop rule and solving the differential equation, we're able to get the formula at the top. Rearranging the equation, we find that the slope of a plot of log delta V over delta V naught versus T will lead us to the value of RC. In our experiment, the slope is negative 0.1667, and taking the negative inverse of that, we can compute the RC value, which is 5.9988 seconds. Note that this is approximately equal to the theoretical RC value, where we multiply the resistance with the capacitance, 30 ohms multiplied by 0.2 farads, which is 6 seconds. There are also some additional questions. What if we are doing this lab in real life and we use an actual ammeter? In this case, since the ammeter in the ideal simulation does not have any resistance, but an actual ammeter has some small amount of resistance for measurement needs, then when we measure the potential differences across other resistors, we would have got smaller results. Similarly, the current we measured in the circuit would also be smaller since there is extra resistance from ammeters. What if we did this lab with a real battery, and how quickly would the capacitor reach full charge by directly connecting to a battery? In an ideal model, the battery can be said to have no internal resistance, so the capacitor can reach full charge immediately, but a real battery has some internal resistance, and it will take longer time to charge a capacitor even if there is no resistor in the circuit. This is the end of my video report. Thank you for watching.